Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on November 19, 2025, just yesterday. It introduces a benchmark called VR Bench and shows that with supervised fine-tuning, video models can reason through maze solving better than leading vision language models, and that diverse sampling at test time boosts reliability by about 10 to 20%. The paper is titled Reasoning via Video, the first evaluation of video models' reasoning abilities through maze-solving tasks. And, as we will see, treating video generation itself as the reasoning process opens up some surprisingly powerful new ways to handle complex spatial planning. Also, the authors shared a GitHub repo for VR Bench. There you'll find the full benchmark code, maze and puzzle game implementations, dataset generation and video rendering tools, VLM evaluation scripts and configs, example usage for each game, plus texture skins so you can customize environments and run your own experiments. Figure 1 presents the whole VR Bench idea, showing how maze-based video puzzles turn into a testbed for spatial reasoning. The top band in panel A illustrates 5 maze types, from simple grids to 3-dimensional layouts and Sokoban-style pushing puzzles, so models must plan in varied worlds. Panel B sketches chain-of-frame reasoning, where the model reasons by predicting the next video frame step by step instead of the next text token. Panel C compares different video and vision language models on exact match, success rate, precision rate, and step deviation, which together capture how accurately and efficiently they trace the optimal path. Panel D then highlights stress tests for robustness, including difficulty jumps, texture changes, switching maze families, and sampling multiple attempts at test time. Figure 2 shows how the maze worlds get harder and visually richer, which is crucial because models must generalize beyond a single clean layout. The full grid of panels can try simple black and white grids with noisy traps, Sokoban-style puzzles, and game-like textured environments. Difficulty rises by adding larger mazes, more branches, and obstacles, while varied textures stress whether the video model truly understands geometry instead of memorizing appearances. Table 1 makes the core performance point clear. The fine-tuned video model WAN-R1 dominates both vision language models and other video generators on maze-solving quality. The table summarizes 4 metrics: exact match, success rate, precision rate, and step deviation across 5 maze types. WAN-R1 reaches perfect success on the trap and 3-dimensional mazes, and it keeps paths much closer to optimal, so it solves puzzles both reliably and efficiently. The highlighted delta row shows very large gains over its own base model, especially on exact match and precision, which signals that supervised fine-tuning really unlocks effective video-based reasoning. Table 2 shows that the fine-tuned video model keeps maze layouts stable while also following the rules more faithfully than other generators. Maze fidelity measures how unchanged the static maze background stays across frames, so higher scores mean fewer glitches or deformations. Vision language model score reflects rule compliance in motion and interactions. WAN-R1 consistently ranks near the top on maze fidelity and achieves the highest rule scores across all maze types. Alright, wrapping up, 2 takeaways stand out. Treating video generation itself as the reasoning process lets models outperform strong vision language models on tough spatial planning, and supervised fine-tuning plus diverse sampling turns generic video generators into surprisingly reliable maze solvers. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.